Hey Bio Team. So you guys have learned that biologists studying evolution care about the frequency of dominant and recessive alleles in the gene pool. So here we'll represent the frequency of dominant alleles as the letter P, and we'll represent the frequency of recessive alleles as the letter Q. And so while these frequencies can change over time or change across different populations, the frequency of dominant and recessive alleles will always add up to 100%. So for example, if 80% of the gene pool was made of dominant alleles, then we could assume that the other 20% of the gene pool was made of recessive alleles. So what's useful about knowing allele frequencies is that you can use them to predict phenotype frequencies. For instance, if you wanted to calculate the likelihood of a homozygous dominant child being born from this gene pool, you can take the chance of one dominant allele being drawn from the gene pool and multiply it by the chance of a second dominant allele being drawn. And you can do the same to calculate the frequency of recessive individuals being born. You just multiply the chance of one recessive allele being drawn by the chance of a second recessive allele being drawn. And last, you can calculate the frequency of a heterozygous individual being produced from the gene pool simply by multiplying the odds of a dominant allele being donated by the odds of a recessive allele being donated. The only caveat is that a heterozygous individual can be produced in two ways. It could be produced by a dominant allele being donated from mom and a recessive from dad, but it could also be produced through the other way around, a recessive allele from mom and a dominant allele from dad. So to calculate the total frequency of a heterozygous individual, you'd need to add these two possibilities together. So all of these possibilities should add up to 100%. Should make the entirety of the population. There aren't any other options. So what biologists have done is they've simplified this idea into something called the Hardy-Weinberg Equation. That is, they've taken the idea that the frequency of homozygous dominant individuals plus the frequency of heterozygous individuals plus the frequency of recessive individuals should all total up to 100% of the population. The only thing to note is that some of the math has been condensed. So this equation is a useful tool for biologists to have. Let's say that biologists notice that 16% of offspring are being born in a population with a recessive trait like blue eyes. And they want to determine what the frequency of a dominant allele and recessive alleles are in the gene pool. Well, what they're observing is that the frequency of recessive individuals is 16%. In other words, they know that the odds of the child receiving one recessive allele, Q, times the odds of them receiving another recessive allele, Q, or Q squared, is equal to 16%. So then if the biologist wants to solve for the frequency of this recessive allele, they just take the square root of both sides, and what they'll find is that the frequency of the recessive allele in the gene pool was equal to 40%. And sure enough, to check the math, if you were to take 40% chance of receiving one recessive allele times 40% chance of drawing a second recessive allele, you would produce a homozygous recessive individual 16% of the time. So if we were going to label our gene pool, then we would say that the frequency of the recessive allele in the gene pool is 40%. And as for the frequency of the dominant allele, well, if 40% of the gene pool is recessive, then the other 60% must be dominant. And so that's it. At this point, you guys have some practice problems that'll let you play around with this. We'll see you next class.